Hey guys, so let's discuss the problem of a car on a banked curve. Now by banked curve we mean that the car is on a curved path and the curved path makes an angle, let's say theta, with the horizontal. So a good example I used this plate. So so this is like a banked curve, right? So the car is moving around on a banked curve and we're going to assume that up or down the path there is no friction, so we'll assume that it's frictionless. Okay, and the car, let's say that this is the car, so let's draw the forces acting on the car. There's the normal force on the car, okay, and then weight is down. Okay, these are the only two forces acting on the car. Okay, now one important question in this case, now the car is moving on the path, right, on the curved path, and again, whenever an object is in a curved path, there's a centripetal force, there's a force towards the center. Now the center of this path is this, right? So this is your circular track. This is the center of the track, right? There's a force towards the center, directly towards the center, not down the plane, it's directly towards the center. So the centripetal force is towards the center, right? So it's always towards the center. Now we want the force towards the center. That's going to be our centripetal force. So a question that I ask when I teach this is, what do you guys think? Pause the video and think about this. Which force amongst these two should we resolve in order to get this centripetal force that's towards the center? Okay, so the answer to this is that we should resolve the normal force in this case. Okay, the normal force, because there's a component of the normal force. So in this case, our axes are towards the center and perpendicular to the center. Towards the center and perpendicular to the, so it's like this. This is our axis, right? So we want this force that's towards the horizontal, right, towards the center. That's n sine theta. Okay, so there are two components of. Let's draw another free body diagram over here. So that's your normal force. So there is, and that's the weight. Okay, we want this guy, n sine theta. That's towards the center. We want this guy, and then there is n cosine theta. So if just one more thing. So if this angle is theta, then this angle is also going to be theta. Okay, because again we've discussed this argument before. Because this line is perpendicular to the ground, and this line, the normal force line, is perpendicular to the plane. So if these two lines make an angle theta, any two lines perpendicular to these two lines will make the same angle with each other. So this is also theta. So this is theta, due to which this is n sine theta, and this is n cosine theta. Okay. So the net force in the radial direction is the centripetal force. The net force in the radial direction is just n sine theta. There's only one force, and it's equal to mv squared over r. Now eventually we have to solve for the velocity, okay, and we want to solve it in terms of the simplest variables, like the weight and the theta and the radius of the path. So the equation in the y direction, there's no motion in the y direction, so that's equal to 0. So you get n cosine theta using capital N, okay, n cosine theta minus w equals 0. So you get n equals w over cosine theta. So let's plug this. You can call this equation 2, equation 1. Plug 2 in 1, so you get w over cosine theta times sine theta equals mv squared over r. So W is equal to mg. Okay, so one of the mass will cancel out. So you get mg tangent theta equals mv square over r. So you get v, so the mass cancels out again, so you get v equals square root of r g tan theta. Here's the velocity of the car on a banked curve such that the car is, can go along the path without slipping. So without slipping up or down. So remember, we assume that this is frictionless. We'll solve with friction in other videos, but this is the velocity. It's again independent of the mass, depends on the radius of the path. The radius is of course this distance, right, from the center to this distance from the center to the car. Okay, and tangent theta, it depends on the angle theta. This can be a good application for this can be a very icy road. So when you have let's say places where there is a lot of snow, you can have a curve. When you take an exit from the highway, the paths are usually curved. The roads are usually banked, right, and curved as well. So this equation can be used in a very good approximation for those roads when they're very icy, so that you don't have friction. So even when you don't have any friction, you can still go around that curved path. So the surface of this plate is also very slippery. So this equation can be valid for this guy, for this plate also. So if you have a very icy road, you can still go around the path, around the curved path, without any friction, if you have because you have the normal force, and n sine theta will help you do that. Okay, so n sine theta is the guy that saves you if you don't have any friction on the surface, between the two surfaces. Okay, so this was it for the car on a banked curve. Thank you for watching. If you have any questions, post them in the comments. Bye.